Let's solve some examples involving joint distributions. The first one is a bivariate distribution x and y, and part A wants us to find the marginal density of x and the mean and variance of x. Let's take a minute to study the joint density. So we have the plane of x and y as you see in the figure. The limits on x are 0 and 1, but interestingly the limits on y are 0 and x. So that's why you see that 45-degree line on the plane of x and y, and only on the lower half, the half where x is greater than y, do you see a non-zero density, and on the other side the density is 0. So let's proceed with finding the density of x, which is nothing but integrating out y from the joint density. So that's what we would do. We would integrate out y. Now the limits of y depend on x, so that's what we are doing here in the integration. And if we do the calculus right, the density of x, the marginal density of x, is simply 4x cubed between 0 and 1. And it's a good idea to check that it is a legitimate density function. So we need to verify that it's non-negative and it integrates to 1, which it does. Now let's use this density function to find the mean and variance of x. So we simply integrate the density function multiplied by x, and that gives us the mean as 0.8, and the variance, it's more convenient to use the expression for variance as mean of x squared minus the square of the mean. So that's what we have done here, and the variance comes to 2 divided by 75. Let's move on to parts B and C. So well, we need to do one more thing in part A. We need to find the marginal density of y and its mean and its variance. So we proceed similarly, but here there is a little bit more complication because of again the limits on y in which the density is defined. So this variable upper limit we can take care of with the help of the indicator function. So we split the integral between from 0 to y and then y to 1, and the first one is 0, and if we do the integration correctly, the answer should be 4y times 1 minus y squared, and that is defined between 0 and 1. And again, like we did for x, let's make sure that this is a legitimate density function, and which it is. You can integrate it and you'll see that it comes to 1. The mean of y would again be the integration as you see on the screen, and it comes to 8 over 15. And the variance, likewise, if we go through the math, it should come to 11 over 225. Now we need to find in part B the correlation coefficient between x and y. So for that we first need to find the expectation of the product xy. So EXY comes to, by carefully putting the limits on x and y, to 4 by 9. If you'd like to pause the video, just make sure that all the steps are clear. And then the covariance sigma xy, which is EXY minus EXEY, that comes to 4/225, and the correlation coefficient, which is the ratio of the covariance and the product of the standard deviations, that comes to about 0.49. There's a part C to this problem, and that is to find the conditional density, the conditional CDF, the conditional mean, and the conditional variance of x given y is at its mean. So the first step is to find the conditional density. So let's start with the definition. So fx given y is equal to mu y is simply the ratio that you see on your screen, and if we carefully plug in the values, we should get it. In the previous part, we have already found the density of y, so we need to evaluate it at the mean because that's the conditioning, and plugging in the values of the mean, we get fy at mu y is 1.527. So we carefully use the formula for the joint density function, divide fxy at x comma mu y by fy at mu y. So the answer is 2.795x. And now the limits of x, we have to be careful. The limits on x are 8/15 on the left and 1 on the right, because x can never be less than y. If it's, as I said, it's a good idea to verify that this integrates to 1, and if we do the integration, it does. Now the conditional CDF, the most straightforward way is to just integrate the conditional PDF, and that's what we do. And so that is simply the integration. Just make sure that there is no density to the left of 8/15. So the CDF starts at 8/15. The expression between 8/15 and 1 is given in the second equation, and at 1 the conditional CDF attains the value of 1. Finally, the conditional mean and the conditional variance of x given y is at its mean. So we again use the basic definition. The conditional mean is the integration of x times the conditional PDF, and if we do it carefully, it comes to about 0.79. The conditional variance, we take the approach that the conditional variance is the expectation of x squared conditioned that y is at its mean, and we already have the expectation of x that y is at its mean. So first we find the e of x squared given y, and then express the variance as ex squared minus the square of ex, both conditioned on y is equal to its mean, and that number comes to 0.018.